Hello friends, I am Rajvi Trivedi. Today I am going to teach you about the probabilistic and randomized algorithm. So, first of all, we understand what the idea behind this probabilistic and randomized algorithm is. We build algorithms using a random elements so as gain improved performance. For some cases, improved performance is very dramatic, moving from intractable to traceable. Often, however, there is some loss in the reliability of results. Either no result at all may be produced, or an incorrect result may be returned, or for numerical results an approximate answer may be produced. Because of the random element, different runs may produce different results, and therefore the reliability of results may be improved with multiple runs. So let's first see. These are the contents of the video. Okay. First of all, we are going to learn overview on randomized and probabilistic algorithm. Basically, algorithms that make random decisions during their execution are known as randomized algorithm, such as quicksort with a random pivot, and probability theory is to analyze the behavior of algorithm. Example for that is determining the probability of a collision of a hash function. So this is a flowchart. This is a structure of the randomized and probabilistic algorithm. Let's take a closer look on each one of this flow. So first of all, randomized algorithms. Think why we need randomized algorithm. Randomized algorithm can solve many NP hard problems. May be easy to solve for typical inputs. Other than that, one approach is to use heuristic to deal with pathological inputs, and another approach is to use randomization of inputs or of algorithm to reduce the chance of worst case behavior. Next we see the probabilistic analysis of algorithm. Now let's take a look why we need probabilistic analysis of algorithm. Naturally, if algorithm makes random decisions, performance is not deterministic. Also, deterministic algorithm behavior may vary with inputs. Other than that, probabilistic analysis also lets us estimate bound on behavior. There is a variety of behaviors associated with probabilistic randomized algorithms. Algorithms which always returns a result, but the result may not always be correct. We attempt to minimize the probability of an incorrect result and using the random element. Multiple runs of the algorithm will reduce the probability of incorrect results. This type of algorithms are known as Monte Carlo algorithms. Now, the algorithms that never returns an incorrect result but may not produce result at all on some runs. Again, we wish to minimize the probability of no result, and because of the random element, multiple runs will reduce the probability of no result. This type of algorithms are known as Las Vegas algorithms. Last we see Sherwood algorithms. Algorithms which always return a result and the correct result, but where a random element increase the efficiency by avoiding or reducing the probability of worst case behavior. Useful of algorithms which have a poor worst case behavior but a good average case behavior. This type of algorithms are known as Sherwood algorithms. Next, we are going to see about the random numbers. The random element required by probabilistic algorithms is provided by a random number generator. Of course, this do not generate numbers at random. Only a truly random processes such as radioactive decay could do this. Random number generators have been devised to generate sequence of numbers which behave as though they were random, in that they pass various tests of randomness. Such sequences are sometimes called pseudo-random. These are variety of methods have been proposed. These all generate numbers in a specific range and require an initial element called the seed to begin the generation. Each number in the sequence is computed from its predecessors. Note that this type of methods have several disadvantages because numbers are generated from predecessors. If a number reoccurs, then the sequence cycles repeatedly. It is intended that different choices generate different pseudo-random sequence. But if a choice coincides with an entry in any sequence, it will generate the remainder of this sequence. The analysis of the randomness and reliability of this pseudo-random sequence is in general very difficult. To generate the random number, take the example of middle square method. Consider 4-digit numbers and repeat the following. Square the numbers and take the middle 4 digits of the square. So, let's take an example. For example, begin with number 1, 2, 3, 4. The square of this number is 1522,756. Take whole square number's middle number, which is here 5227, as next entry. Square A and its square is 27321529. Next number is 3215. So get the generated sequence as 1234, 5227, 3215, 3362, 3030, 1809, and so on. Note that this is not a reliable method because for some seeds it will repeat itself fairly quickly and the selection of numbers may not be very uniform in the intervals as zeros tends to be propagated. Take another example of linear congruence method. Linear congruence methods are widely used. They require the choice of two numbers, m, which is the divisor for the congruence, and b, which is allow us to generate new instance. Then, for any seed A, we generate the next number in the sequence as shown mod formula here. The choice of M and B is critical. M should be large and there are rules for choosing a suitable B. So, see the example how linear congruence method can generate the random sequence again. The analysis of the randomness of this sequence is difficult. Other than this, the methods we can use the additive congruence methods to generate the random methods. Now, let's see Monte Carlo of probabilistic randomized algorithm. Can you recall the behavior of the Monte Carlo? Let's recall it. Algorithms which always returns a result, but the result may not always be correct. We attempt to minimize the probability of an incorrect result, and using the random element, multiple runs of algorithm will reduce the probability of incorrect results. And next in this video, we are going to see the example of Monte Carlo algorithm. There are two examples which I cover in this video, which are majority elements and matrix multiplication. So, okay. So first we see majority elements example. There is an array A of n natural numbers has a majority element n if the number of occurrence of n in A is greater than n divided by 2. So the question is, how would you decide whether an array has a majority element using a deterministic algorithm, and what is its complexity? By choosing an element at random and testing to see if it is a majority element, we get a probabilistic algorithm. So, see the algorithm carefully. Here, random number 0 to n minus 1 is a uniform random selection of integers between 0 and n minus 1. Notice that this algorithm returns true exactly when it has selected a majority element, but that it may return false even if there is a majority element. However, if there is a majority element, then the probability of returning false is less than 1 divided by 2. Since a majority element occupies more than half the array, we call such an algorithm true biased and half correct. Because of the random element, repeatedly running this algorithm will increase our confidence in the result. If it ever returns true, then there is a majority element. If after m runs every result is false, the probability of having a majority element is less than 1 divided by 2 raised to capital M, which you can see in this algorithm. Okay, here is another example of Carlo algorithm. Recall that the standard way of multiplying n cross n matrices A and B to get the result C as given first formula you can see here. The time complexity of this is the order of n cube. After that, we also studied that Stetson's algorithm that has complexity of order of n raised to 2.81. There are also some further algorithms of increasing complications and computational overheads have been proposed with the complexity varied down with n raised to 2.376. Now see, here is a Monte Carlo matrix multiplication algorithm to get a matrix C, which is the result of matrix A and B with complexity of order of n square. Give attention to this Monte Carlo algorithm. How this algorithm has the complexity order of n square? Because it returns true whenever AB equal to C. The product of A into B equal to C. We can show that it returns false with probability at least 1/2 when A product B not equal to C. Again, multiple runs of this algorithm will therefore increase the reliability of the result. Okay, these are some other examples. The Monte Carlo technique has been used to provide probabilistic algorithms for a range of applications, which includes such as testing the primality of numbers. Deterministic primality testing is computationally difficult, but believed not to be NP complete. Second is deciding set equality, and the last and third is applications in cryptography. Okay, so next we are going to see Las Vegas probabilistic randomized algorithm. Now let's recall the another probabilistic randomized algorithm, Las Vegas. Algorithm that never returns an incorrect result, but may not produce results at all on some runs. Again, we wish to minimize the probability of no result, and because of the random element, multiple runs will reduce the probability of no result, that is known as Las Vegas algorithm. Las Vegas algorithms may produce traceable computations for tasks for which deterministic algorithms are intraceable even on average. However, we cannot guarantee a result and there is no upper bound on the time for a result to appear, but the expected time may in fact be small. Typically, Las Vegas algorithms are used to explore a space of states, some of which are the successful states we seek. Las Vegas algorithms use some random choices to move about the space rather than computing at each state a new state to move to. This is likely to be successful if the proportion of successful state in the state space is fairly high, and will lead to an improved efficiency if the computations of next states are difficult, or if systematic exploration is not necessary. However, some random choices of next state reach states where no further moves will lead to a successful state, but we can of course run an algorithm again and different choice will be made. Let's see more in example with 8 queens problem soon in video. The 8 queen problem is a well-known algorithmic task where we are asked to place 8 queens on a chess board with no queen attacking another. A queen attacks other pieces in the same row, same column, and along its diagonals. So here you can see the figure. This is one of the possible solution we can put the queens. The classic solution is via backtracking. Place the first queen in the top left corner. Now with some non-attacking queens in place, place a queen in the next row. If it attacks previous queens, move it across the row, square by square. If there is no suitable position in this row, then move the queens in the immediately previous row on one space if possible. If neither row leads to a required arrangement, move the queen in the previous row by one space, and etc. In fact, this returns a solution after examining only 114 of the 2057 states, which is a very good result. Now try to solve the 8 queens problems using the Las Vegas algorithm. Suppose that k rows between 0 to 8 have been successfully occupied and take initially k equal to 0. Okay, if k equal to 8, then stop with success. If not, then we have to occupy next row k plus 1. Calculate all the possible positions of this row for those which are not attacked by already placed queens. If there are no such places, then fail. Otherwise, choose one such place at random, increment k, and repeat the same. Notice there is no backtracking here. If at any point we cannot place a queen, we fail. However, we can repeat the run, and because of the random element, we will get a possibly different arrangement. It seems in Las Vegas algorithm, this problem can be calculated with the probability of success of this random placement is 0.1293. This may seem low, but it means that a solution is obtained one time out of 8 simply by guessing. The expected number of states explored is approximately 56 compared to 114 for the deterministic backtracking solution. The reason for this is that the solutions of the problem seems to be in some sense unsystematic or random arrangements. In fact, we can do better by combining random placement and some backtracking. First fixing some queens at random and then completing the arrangement by backtracking. If two are placed in the first two rows at random, then expected number of states explored to find a solution is only 29 factorial. The Las Vegas technique has been used to provide probabilistic algorithms for a range of applications which includes efficient factorization of integers, breaking symmetry in networks of processes. Now, let's understand the last method of probabilistic randomized algorithm, a Sherwood method. Recalling the behavior of the Sherwood algorithm, this algorithm always returns a result and the correct result, but where a random element increases the efficiency by avoiding or reducing the probability of worst case behavior. This is useful for algorithms which have a poor worst case behavior but a good average case behavior, and in particular can be used where embedding an algorithm in an application may lead to increased worst case behavior. Next is the example of quicksort pivot selection problem solving using Sherwood methods. Quicksort is a sorting algorithm with worst case behavior of order of n square but average case behavior of order of n log n. The problem is that we cannot guarantee very uneven splits of the list by using pivots. Indeed, systematic choice of pivots, let's say the first element, can lead in certain applications, like for when almost sorted lists tend to be supplied to worst case behavior. This is undesirable. So, now let's see, how do we find the suitable technique using Sherwood methods? We select pivot at random. We can do this by modifying the quicksort algorithm to choose a random pivot, or if modifying the algorithm is not feasible because it is too complicated or we don't have the source code, then use stochastic preconditioning, like randomly shuffle the input before supplying it to the algorithm, which will have a deterministic choice of pivot. These Sherwood techniques are useful in searching, selection, median finding, sorting, hashing, and more generally, where worst case behaviors and average case behaviors differ, and worst case behavior arise from systematic choice with randomization can avoid. Okay, now let's see probabilistic algorithm with example of numerical integration. Probabilistic technique can be used to solve numerical problems by giving approximations to the result. As we know, repeated runs give increased accuracy of the result. Now consider calculating the integral. The shown formula here is the area under the curve f. Suppose that we know that for x belongs to 0 to 1, where function f is in between and including 0 and 1. Then the following probabilistic technique approximation the solution. This is the algorithm where we select points in the 0, 1 square at random and test whether or not they are below the curve. The result is the proportion of those below the curve. Another probabilistic method is to choose points at random on the x-axis, calculate the value f of x, and take the average of all these cases. These methods usually do not provide a fast converge to result, and for simple integer, standard approximation methods like trapezium method or Simpson's method are better. However, occasionally functions may perform badly on a systematic method, especially if they have multiple periodicities. For multiple integrals in higher dimensions, probabilistic techniques can prove useful. Okay, so now let's see the another example of probabilistic algorithm, which is universal hashing. Let's take a look on universal hashing using probabilistic algorithm. Okay, in general, hashing is used when one would like to maintain a set of items with fast lookup, and on average its complexity is order of 1 insertion and lookups. Now using probabilistic algorithm Universal hashing is a finite collection H of hash functions that map a given universe U of key into the range of 0, 1 up to m-1 is said to be universal if for each pair of distinct keys k, l which belongs to U, the number of hash function h which belongs to H, capital H, for which h of k is equal to h of L is at most mode of h divided by m. Here, at runtime, pick the hash function that will be used at random from a family of universal hash functions. So, we can conclude that universal hashing gives good average case behavior if key k is in table. Expected length of chain containing k is at most 1 plus alpha. So we are at the last part of the video, the conclusion of video. Here in this video we learn about the randomized and probabilistic algorithm with detailed explanation and example of Monte Carlo, Las Vegas and Sherwood algorithms. In examples we understand how the time complexity affects when we use the randomized and probabilistic algorithms at the place of the classic algorithms. Thanks for watching this video. Thank you.